start the video now. I've got a link to actually the video I showed the lecture before last and this video up on the course website. Also notice here that he was talking about this transverse mode where the vibration, the amplitude of the vibration is perpendicular or transverse to the direction of propagation. With a mechanical, with the spring, you can also set up what are known as longitudinal waves. You know, if you had oscillated it back and forth, then you wouldn't have a vertical vibration, a vertical amplitude variation, but it would, what you would see is compression and expansion propagate along the spring, and that would be a longitudinal wave as opposed to a transverse wave. Okay. So we talked about these standing waves. Last time. Let's see. And right. What did we talk about last time? So first we talked about voltage reflection, and then the voltage reflection coefficient gamma. We got into standing waves, and we talked about match loads, and then also other types of loads, in particular the open circuit load or open termination, the short circuit load, and then the general case as well. We want to kind of continue that discussion, talking about the case in which there's a load, and then we have a standing wave. So this is our load impedance, and we're considering the lossless line case still, where the alpha term is 0, or our propagation constant gamma is entirely imaginary, is equal to J beta. And then, so we're considering a length of line L, but remember now that we've defined Z is going to our right, and we've put our origin now at the load. So this would actually be back at this point. It's just a general point. L back from the load would be where Z is equal to minus L. And our transmission line has a characteristic impedance, Z0, which again for a lossless line is entirely real. And then, we can define a voltage here, and our current is defined as going to the right, but the ratio of that voltage to current is an impedance. And it's actually going, because our voltage and current are changing along this line, our impedance is actually a function of distance, Zn of L. Again, at low frequencies, if these are a pair of wires, if you measured the impedance here, it would be equal to ZL. But something is different at these higher frequencies, where it takes time for the voltage to travel and the current to travel down our transmission line for that propagation to take place. So we found these voltages and currents last time. And remember, this now is a sum of two parts. It's the right propagating wave and the left propagating wave that sets up the standing wave. And we saw last time that with our voltage reflection coefficient, that the voltage is equal to V0, that's the amplitude of the right propagating wave, And then the ratio of the amplitude of the left propagating wave to V0 is gamma, our voltage reflection coefficient. Now, again, for our right propagating wave, remember we've always had minus j beta z here for this first term. But now z is minus L, so that's why this appears as a positive term. That's the numerator. And then we had an expression for the current. It's similar, except it's this, we're subtracting the second term because the current is going to our left. And it's divided by the characteristic impedance of the line, okay, to get the current. So I'm going to skip a couple of steps of algebra here, but you see that our V0s can cancel. I'll have this 1 over Z0 becomes a Z0 out in front. The other thing I'm going to do to simplify this a little bit is actually multiply the numerator and denominator by e to the minus j beta L. So when I do that, that gives me a 1 here. E to the plus j beta L times e to the minus j beta L is e to the 0 or 1. And then the second term then will become e to the minus j 2 beta L. And then the denominator becomes 1 minus gamma e to the minus 2 beta L. Again, where we had beta is a function of frequency. It also depends on the characteristic inductance and characteristic capacitance or transmission line. And then characteristic impedance is L prime over C prime. And this is the lossless case where R prime and G prime are both 0 in our transmission line model. And where gamma, our voltage reflection coefficient, is ZL minus Z0 over ZL plus Z0. And again, although our characteristic impedance C0 is real, ZL can be anything. It could be an inductance or a capacitance, a pure reactance. It could be a resisted load. Remember, we looked at the special case where if ZL is equal to Z0, that's the matched case. There is no reflection. Gamma is 0. There is no reflection in that case. And then the impedance along the line is equal to the characteristic impedance everywhere. It doesn't vary in that matched load case. It's not a function of distance. So we can rewrite this as and actually I think this is maybe one of the homework problems. There's a little bit of algebra here. Tangent of beta L over Z0 plus J ZL tangent of beta L. And that just comes from actually substituting this expression for gamma into this expression for Zn, and then doing some algebra, multiplying numerator and denominator by ZL plus Z0 and simplifying. You get these exponential terms that become cosine and sine using Euler's formula. So there's a few steps of algebra that I skipped there. Now, and often we try to match the load to the line so that we don't get this standing wave set up, and our input impedance is equal to Z0. What that often means that we have to do, given a particular load, is maybe put something in parallel with the load, or put something in series with a given load, so that we change the load impedance so it's equal to Z0. So it's called impedance matching. So the question is how to do that. Often we could do that with a series of, with some combination of inductors or capacitors. But there's something interesting here that when we look at the input impedance with the open circuit, and we'll look at the short circuit case first, that you can make a transmission line, a piece of transmission line, look like an inductor or a capacitor. So just a length of transmission line, it has to be, you don't need, it can actually replace a physical or inductor or capacitor. And so this is often used, again, to do impedance matching, which we'll talk about next time. But this does have application. So when is a short not a short? When it's a transmission line or at high frequencies, where it may look like an inductor or capacitor. So in this case, with the short circuit, ZL is 0, so gamma is minus Z0 over plus Z0, or just minus 1. And our expression for Zn of L reduces to plus J Z0 tangent over beta L. And that's actually this plot here, a plot of the input impedance as a function of L, where Z is actually, this is the positive length, so Z is actually, this is from the load back to the source. So this is kind of time, not time reversed, but reversed in space. So if I flipped it this way, this would be my load, and I'm going back this way. Again, at the load, you notice the input impedance is 0. It's a short circuit at the load. The rest of this is actually just a plot of this tangent beta L function, where this is now in, remember, beta is 2 pi over lambda, so L here is in wavelengths. A quarter, L is equal to a quarter wavelength back from the load, a half wavelength, 3/4 wavelengths, and a full wavelength. And this just repeats because our tangent function is periodic. So I'll talk more about this in just a second. The other case is for ZL equal to infinity. That's the open case. Gamma is plus 1, and in that case, Zn of L is minus J Z0 cotangent of beta L. You have 1 over the tangent, which becomes the cotangent. So again, this is a couple things to note here. The input impedance, now, again, this is with the short circuit. So there's nothing in here that looks like an inductor or a capacitor. I've got a piece of coax, and I've cut it and then just run a wire between the center conductor and the shielding on the coax, okay, to get this short circuit conduction, or the short circuit connection. Or with strip line, I have to do the same between the piece of strip line and my grounding plane, add a short. That's this first case. The second case is, got a piece of coax and I just cut it at a certain length L. notice that this is an entirely reactive impedance. There's no real part. Okay, it doesn't look like a resistance. This is not, so over a range of L, this looks inductive, but tangent can be either positive or negative, right? Impedance of an inductor is plus JX, J omega L. Impedance of a capacitor is minus JX. Okay, so, but since tangent can go either positive or negative, when tangent is positive, Zn looks like an inductor. When it's negative, it looks like a capacitor at a certain distance from the load. And here we have just the opposite. So, here I'm at the load, measuring the input impedance right at the load. That's a short circuit. But between a distance of 0 to a quarter wavelength back from the load, I measure an inductive impedance, purely reactive. So in this case, the voltage and current would be 90 degrees out of phase. That's what the J does for us. And the inductance, I can get any value of inductance I want between 0 and infinity, actually. This would be any value of inductive reactance. And the next quarter wavelength interval between lambda over 4 and lambda over 5, back from my short circuit, is capacitive. Again, with any negative capacitive reactance I want between minus infinity and 0, and then it's periodic at lambda over 2. And then this just repeats forever. So in most applications, when you're using this for impedance matching, you try to use as short a length of line, as short a length of line as possible. So between 0 and lambda over 2, you can get any desired value of inductance or capacitance. Okay, so this is called, these things are called transmission line stubs, because they can also often be put it in parallel with a special coax connector, a T-type connector that actually allows you to just hang off a piece of transmission line. Actually, this is the short circuit case. The other figure, both of these are in the book. This is the open circuit case. The difference is at the load, at a distance of 0 from the load, with the open circuit case, we get an infinite impedance, right? But then you see the same type of behavior. A quarter wavelength back from this open circuit, it looks like a short circuit. Just like the short circuit case, quarter wavelength back looked like an open circuit, had an infinite impedance. Same thing here. Looks like a short circuit, a quarter wavelength back, and then it's periodic with a period of lambda over 2. So, again, with the short case, ZL equal to 0, Zn of L is plus J, Z0 tangent of beta over L, where, and Z0 is the square root of L prime over C prime, and beta is omega square root of L prime C prime. So Zn looks like an inductor in the range 0, L is between 0 and lambda over 4. So this is the previous figure. In this range, we've got this plus J thing. Looks like a plus J thing, so it looks like an inductive reactance and looks like a cap. And the next quarter wavelength segment. So this transmission line, this short circuit transmission line, can be used in place of an inductor or capacitor when building filters or doing impedance matching. And we'll see applications of that, I believe, next lecture, okay, where we do this. And an open termination can be used similarly. Here with the short circuit, during the smallest segment, you actually get an inductive impedance. With the open circuit, during the shortest segment, that first quarter wavelength, that looks capacitive. But you can use either. Now, it doesn't have quite the same frequency dependence as a real inductor. You know, a real inductor is J omega L, right? This is J, this thing. There is frequency dependence in here due to beta, but it's like the tangent of the frequency. Now, over a short distance, tangent omega is approximately proportional to omega. So over a short distance, you know, maybe lambda over 10, length is less than lambda over 10. This acts like an inductor. Okay, so it doesn't act like an inductor over a wide range of frequencies. It doesn't have the same frequency dependence, but at a particular frequency, you know, it has a JX, positive JX impedance, just like an inductor at a frequency would have. So in some applications where if you're just transmitting using a small range of frequencies on your transmission line, again, this works. This substituting this piece of transmission line for an inductor actually works. Turn this off now. Hold on, maybe I bring it back up. I'm going to work through a few problems here in just a second. But so let's talk a little bit about, you know, we've looked at, you know, determining the characteristic impedance if we know L prime and C prime. And right now, I think what we've done is, you know, you go to the coax manufacturer's website and find those. We actually got some theoretical equations in our textbook from the previous section for coax and strip line for determining L prime and C prime, and also G prime. You know, based on the geometry of the coax and the strip line, you know, the width of the conductors or the radius of the conductors, the separation between them. But, you know, typically you would go to the coax manufacturer's website and they would provide those for you. We can also measure Z0 and then beta by making impedance measurements. And the way we do that we measure the short circuit which, using the same notation in the book, calls this, it uses a subscript IN. This is the input impedance, and then a superscript capital SC for short circuit. And open circuit ZN OC input impedance. So we can use a device in the lab. You know, if we apply a voltage, measure the voltage at that point, determine the current at that point, we can take that ratio and actually get the input impedance. Theoretically, these are equal to, we've got the expressions for them, plus j z0 tangent of beta L and Zn, the open circuit case, is minus j z0 cotangent of beta L. Well, someone noticed that if you take the product of these two measured values, the theoretical equations, here we've got tan beta L, here we've got cotangent beta L, which is 1 over tangent. So the tangent-cotangent product goes away. Here we've got plus j, here we've got minus j. That product is equal to 1. So the product of these two will be equal to z0 squared, or z0 is going to be the square root of the product of my two impedances. So I have to set this experiment up first with the short circuit termination. Well, it doesn't matter which one you do first, but once with a short circuit termination, and then with an open circuit termination, again using the same length of line. And notice here, it doesn't matter what line length is used, as long as it's the same, the tangent-cotangent product will cancel. And then the square root of that product is the characteristic impedance of the coaxial line. So I can measure this and compare to my theoretical results if I want. Similarly, the ratio of the short circuit impedance divided by the open circuit impedance, theoretically, that's minus tangent squared of beta L. And the J0s cancel out. I have the minus sign left over. Tangent divided by cotangent, though, is 1 over cotangent is back to tangent again. So I get tangent minus tangent squared of beta L here. Or tangent of beta L is equal to the negative of the ratio of the short circuit to the open circuit input impedances. And again, although these are individually, these are reactive, J, X, the J's cancel out, so that ratio should be entirely real. So what does this allow us to do? Well, it allows us to determine this tangent beta L thing, right, from that ratio. Okay. The inverse tangent then, or arc tangent, would give me beta L. If I know the line length, which I can measure with a ruler, then I can get beta, and then we know the propagation velocity along the line is omega divided by beta. So I can get the propagation speed along my coaxial cable as well, which again, in the coax we worked with so far, it's been around 2/3 the speed of light, not quite as fast as the speed of light, but we can measure the propagation velocity. Okay. Let's take a look at a couple of problems from
with each mode, there's a particular frequency that I have to vibrate at in order to create that mode. So one-to-one correspondence between the modes and the frequencies. That's standing waves.
I can copy over the problems, but they're posted on the website, aren't they? Work. Text on. So that is not on. So let's take a look at 315-1. I'm trying to leave some of these relevant equations here on the board. So -1. So it's a lossless transmission line, which is what we've been working with. Characteristic impedance of 50 ohms. So that's what we call Z0, which is standard notation. It's terminated. So this is our load impedance. So this we would have 72 plus J 42 ohms, and then the line is 1.5 wavelengths. So they don't give us the frequency, but they give us the length and wavelengths. What is the input impedance of this length of line? 1.5 wavelengths with a load impedance of 72 plus J42. So here we have to go to our general equation. This one is the one that we want to use, right? So first thing we want to do is determine, and this looks nasty at this point, primarily because ZL is this complex thing. I mean, it's not going to be that bad when you plug it into your calculator. We could do it in general at any wavelength, but let's see what happens. You know, we've got to calculate beta L and tangent beta L. So beta is 2 pi over lambda, and then L here is given as 1.5 lambda. So beta L is 3 pi radians. Fortunately, that simplifies things quite a bit. So, you know, what's the tangent of 3 pi? What's the tangent is sine over cosine? What's sine of 3 pi? Yeah, it's 0, right? That would actually be 2 pi around and then another 180 degrees. So that would be, sine would be 0, cosine would be -1, but we've got 0 divided by -1 or 0. So fortunately, he gave us a case that simplifies a lot. At this distance, then Zn of L is, this case, both these, I'll write down the general equation. Z0, ZL plus JZ0 tangent of beta L over Z0 plus J ZL, tangent of beta L. But in this case, both those tangent beta L terms are 0, and we're left with, here we've got Z0 over Z0, and here we're left with just ZL. So the input impedance at this distance is equal to the load impedance, 72 plus J, 42 ohms. And that would be true at this distance, a distance lambda over 2 longer. So plus 1/2 lambda. So at 2 lambda, at 2.5 lambda, at 3 lambda, 3.5 lambda, we would see this input impedance. But at other distances, you can see something completely different. Because this tangent goes anywhere from 0 to plus or minus infinity. So we get various combinations of the load and characteristic impedance. So let's take a look at, time for one more, I think. Let's go ahead and do one from section 16. I'll do it over here. So my equation's up there. We're all on 3.16-1. So L is 13 centimeters. First thing I want to do is actually write that as 0.13 meters, right, in our standard units. Coaxial cable, characteristic impedance of 75 ohms is open circuited, so we know the load impedance is infinity here. F is 900 megahertz, the frequency. Find the input impedance of this section of coax. So again, nothing attached here to the coax, it's just clipped 13 centimeters, so something about that long, I guess. It gives us the phase velocity is 0.55 c. So this is one of the special cases. It's actually this one we use for the input impedance. This was open circuit. Yeah, ZL is infinite. So that's the minus J Z0 cotangent of beta L. So we're given L. Question is, how do we get beta? Well, it's actually wrapped up in the phase velocity. So the phase velocity is omega over beta, which implies that beta is omega over the phase velocity. So omega is 2 pi f, 2 pi 900 times 10 to the 6. And the phase velocity here on this piece of coax. So instead of giving us beta directly, it gave us the phase velocity, but they're related by the frequency. And then C is 3 times 10 to the 8th. So does someone have a calculator handy?
34.27.
34.27. Now multiply that by 0.13. 34.27, because our line length is 0.13.
4.455.
Say that again.
4.455.
55. Okay, so this would actually be radians. So beta is actually radians per meter. We multiply that by our length in meters, and we get this in radians. So it's a little past pi radians. So the tangent there, that would mean sine is negative, cosine is negative, so the tangent would be positive. So we should get a positive number here for the cotangent, but what's the cotangent of this?
77.34.
Are you calculating radians? It may be.
No, it's 1.35.
1.35. And then so finally, if you multiply that value times Z0 is 75. And then there's the minus J. So 75 times the 1.35 is what?
101.25.
101.25. This would be ohms. So it looks like a capacitor because of the minus J. It's got a negative reactance. I could find the equivalent capacitance actually at this frequency, divided by omega here would give me the equivalent capacitance this thing looks like. All right, that's it for today. We'll continue this. I mentioned at the start of class, we're actually finishing up chapter 3. So we'll finish it on Friday. We've got 2 more lectures. And then we have our first exam in here a week from Monday, or I'm sorry, a week from Wednesday. So we'll review on Monday of next week, and then for our exam on Wednesday.